Okay, our next speaker is Cary Kopczynski. Cary is the CEO and senior principal of his company CKC, a structural engineering firm based in Bellevue, Washington. He provides structural design for major urban projects throughout the U.S. and beyond. Cary is a member of ACI's 318 Building Code Committee, and he serves on ACI's board of directors. He's also PTI's chair of the Technical Advisory Board, which oversees all of our technical committee activity, and he also serves on PTI's board of directors. He's a fellow of both ACI and PTI, and ENR selected Cary as one of the top 25 newsmakers for 2007 for his pioneering work in the use of high-strength reinforcing bar for seismic application confinement. Please welcome Cary.
Thank you, Ted. Excuse me. So, the PT industry has come a long way in the last several decades. When I look back over my own career, I remember not too many years ago when we started a cast-in-place concrete project, the first thing we would do is debate whether or not we should use post-tensioning in the first place. Because back in those days, we were still doing a lot of mild reinforced work. We no longer have those debates. Because if we're designing a cast-in-place concrete structure, almost always, with very few exceptions, at least in my office, we're using post-tensioning. Now, we're using post-tensioning for all of the obvious reasons. I'm preaching here to the choir today because we're all in the industry, but we all recognize that PT does bring a lot of benefit to almost every cast-in-place building project. So what I want to do initially here is walk you through some examples of work that we're doing in my office that illustrate the benefit that post-tensioning brings to a project, starting with 815 Pine. This is a building currently under construction in downtown Seattle. Flat plate concrete. We used PT throughout, including down in the subterranean parking structure. 7.5-inch floor slabs, cantilevers that extend almost to 11 feet. And all of this is accomplished with post-tensioning. We could do none of that with mild reinforced concrete. It takes PT to push the spans out, keep the floors flat, allow long cantilevers. What PT also does on the West Coast is provides a lot of seismic benefit, because in using post-tensioning we reduce the building mass. When the building mass goes down, the seismic loads drop and the core becomes more efficient. This building just finished up in downtown Seattle, the Martin. This is a 24-story apartment tower. By using post-tension flat plate construction, we were able to strip out a number of the columns, eliminate transfer beams, reduce the foundation sizes, and also allow the use of a very high production forming system, which enabled the contractor to finish ahead of schedule. And had we used mild reinforced concrete in this building, we would have had more columns, we would have had transfer beams down at the ground levels. The use of this high production formwork would have been much more difficult, and consequently the schedule would have been extended. So PT brought enormous value to the Martin. The Victoria, just up the street from the Martin, also finished up last year. Another 24-story, 240-foot apartment tower. On this project, we used a drop head around the core, which is a thickened slab section that extends 6 feet off the core walls. And by doing that, we used an 8.5-inch PT flat plate slab throughout all the tower levels. The 8.5-inch slab thickens up to 16 as it approaches the core. And that 6-foot extension off the face of the core allows us to achieve spans to almost 40 feet from the core to the glass. So we eliminated all internal columns. So we have not a single internal column in the building. We have a core and we have exterior columns, which means no transfer beams, no disruption in the lobby, and much more efficient parking. This project, a few years back now, by using PT, we pushed the floor spans out to about 32 feet. We used balcony cantilevers that were nearly 12 feet. And the use of PT enabled us to create a very well-aligned and very consistent column grid that enabled the contractor to use a column-hung forming system, which means the formwork actually hangs off the top of the columns. There's no shoring, there's no reshoring. There's no disruption whatsoever to the trades below. You can follow behind with the cladding. The cladding is within a floor or two of the pour deck, and again, it helps speed up the construction sequence. This project just now nearing completion in Los Angeles. This is a 30-story and a 25-story apartment tower. The taller building obviously on the left, and then a common podium, an L-shaped podium with a pool that you see there in the foreground, and all the amenities that go along with high-end residential living. But this is all, again, flat plate PT. The use of PT reduced the foundation sizes, reduced the column sizes, and very importantly in Los Angeles, reduces the building dead load, which brings the seismic load down, so it creates much more efficiency in the seismic system, none of which would have been true had we gone with mild reinforced concrete, because the dead load would have gone up roughly 25 pounds per square foot, which means larger foundations, bigger shear walls, and all of that. So again, PT brought advantages that were not possible without it. A few buildings currently in design in my office. This is an expansion to an existing complex in downtown Bellevue, which is where my office is. The building on the right with the red cap is an office building. That's actually structural steel with a concrete core. But the building on the left is a combination of hotel and residential, the hotel below and the residential above. And we are using PT flat plate, thin floors, 8-inch slabs in this building. And the use of PT enables us to strip out columns, increase the floor spans, maintain good flat spans, flat floors, minimize deflection, and very importantly, as you transition the tower on the left, which sits over the top of a retail podium and a lobby and a parking structure, it strips out, PT allows longer spans, which strips out the columns, which minimizes transfers and allows more efficient construction below. This building also currently in design, Potala Tower in downtown Seattle. We're using the drop head concept where we thicken the slab up as it approaches the core. It allows the spans to be pushed out to almost 40 feet, so we have no internal columns, and a very efficient and effective way to build a high-rise residential tower, because by taking all of the internal columns out, the space planning is improved, the use of the building is enhanced, the transfer beams are gone, the parking is much more efficient. Parking in a residential building, or any building for that matter, in an urban environment, if it's subterranean parking, can approach $30,000 to $40,000 per car space, sometimes higher. So if you can eliminate internal columns and add some parking stalls, 2 or 3 stalls per floor, very quickly it can pay for a little more slab and material quantities up above. And then finally, the building that we're just starting as of a couple of weeks ago in Los Angeles. These are 2 40-story condominium towers, and we're proposing to use flat plate PT construction with internal cores, and based on the preliminary numbers that we're running, the use of PT again reduces the building mass, which reduces the seismic load, brings the foundation sizes down, reduces column sizes. There are a lot of ancillary benefits to the use of post-tensioning that go beyond just the savings in the floor slab itself. You reduce column sizes, foundation sizes, and on the West Coast, you reduce seismic requirements. So, talking about, and again, I know I'm preaching to the choir here today, but the advantages in the use of post-tensioning: thinner slabs and shallower beams, longer spans and fewer columns, reduced floor-to-floor height. This could be a big one on a tall building, because if we can take 2 or 3 inches per floor out of each level, sometimes we can add 1 entire floor to the stack. And if you're working to a height limit, if there's a zoning height limit, and the goal is to put as many floors into the height limit as possible, post-tensioning could bring that to the table. Or, conversely, if you don't add a floor, you could increase the floor-to-floor height up at the top of the building in the penthouse units, or you can add more space in the retail at the bottom. A lot of benefits in reducing the floor-to-floor height. Better control of deflection and cracking. Those of us in the design business or construction know that a big benefit with post-tensioning is that we profile the cable, we pick up the dead load, and at least in theory, we can bring the deflection down to almost nothing. Now, in actual fact, it never seems to happen quite that way. Even the best intentions sometimes result in a little trouble out in the field. But with PT, we have a lot of control over deflection and cracking. We have smaller columns and foundations because of the reduced mass. And again, because of the reduced mass and weight, we end up with lower seismic loads. So talking now about a debate, quality versus cost. Oop. I'm not sure that slide, no. Let me back up here just a second, talk about a couple of other topics before I get to that. Here's a garden variety PT slab. I'm sure this is nothing new to those of you in the audience. We have a banded plate. We have uniformly spaced strands running up and down on the photo. We typically group those in clusters of 2 or sometimes 3, depending on the PT quantities, and then we have bands running transverse. So it's a typical banded flat plate. We have a lot of versatility with banded plates. We can bury conduit and water lines and all sorts of things. You can see here in this shot, this was one of our projects a couple of years back, but look at the quantity of conduit that can be buried into a PT slab and not compromise the performance of the slab. This is feeding out of the core area, and the conduit then runs off into the various units. We can also bury mechanical ventilation. We've done projects where we've had electrical conduit, water lines, and bathroom exhaust, kitchen exhaust, and dryer exhaust all buried into a floor slab. So these are the exhaust lines that feed from whatever they're exhausting to the exterior of the building. They're typically 1 3/4 inches high, 12 inches wide. We bury those into the middle of the floor slab, and then we try to keep those out away from the bands so that they go over the top of the cables. Sometimes that doesn't occur, so we put them under the cables. But suffice it to say that the versatility of PT flat plate construction allows all of the other trades that follow behind to do their thing well too. The electrician, the plumber, and the HVAC folks. And so now I want to talk about the topic of cost versus quality, and this takes off and corroborates what Mark was saying earlier. The whole issue of, does it pay to build quality? And I want to use an example that comes up frequently in my office. There are a number of things in the process of designing a building that we have no control over. The load factors come straight out of the code. The capacity reduction factors, so-called fee factors, straight out of the building code. So there are a lot of things that we do every day that we really don't have any control over. They're mandated by the building code. But there are a number of other decisions that we make each day that we can exercise good judgment around, and in the process create better value for the owner. An example is a residential balcony. So in some of the projects I was just showing, where we have exterior balconies, cantilever balconies, the code says that we should design those for 60 pounds per square foot of live load. Now what's the first thing that a condominium owner or an apartment resident does when they move in? They go down and they buy the biggest pot they can find, and they put it out on the balcony and fill it with dirt. And then they plant a tree in it. And then when they have a party, they get people out on the balcony elbow to elbow, and so very quickly on that balcony you will have 80 or 100 pounds per square foot of load. The code says we can design a balcony for 60. We don't do that in my office. We tell our clients that it's worth a little extra money. The balconies are a very small percentage of the total square footage. Spend a few extra dollars. We'll put a little more reinforcing in your balconies, and we'll design them for the load that they really will truly experience. And I've never yet had an owner who said no. They said, yes, that sounds like a very good idea. So owners will spend money if they're shown the ROI. Now the same thing is true with encapsulation. This is a topic that Mark touched on earlier. There's been a debate over the last several years about whether PTI should recommend full encapsulation for all post-tension construction. PTI did come out and make that recommendation a couple of years back. ACI has not quite yet rolled in, but they will soon. Nevertheless, as it stands today, designers this moment can design structures that are not fully encapsulated. In my opinion, that's not smart, because the ROI is very high given what it takes to create encapsulation, which is not very much in terms of cost. And these are some samples of encapsulated anchors from various suppliers. They all accomplish the same thing. They protect the anchor, the wedge cavity, and the cable from corrosion. Now if we look at what the cost is, option 1 shows construction cost without encapsulation. So here's construction without encapsulation. In most markets of the country right now for a commercial building, you're plus or minus $200 per square foot to build the building. Your land plus your soft costs, that's the price of the dirt that you're building the building on, plus the permitting fees, the design fees, the taxes, all the other corollary costs that come along, result in about $150. So for the garden variety urban building, you're going to spend about $350 per square foot to build it. The owner will. Not you, but the owner will. Option 2, construction cost with encapsulation. The numbers that we always run in my office show that almost never does encapsulation cost you more than about a nickel per square foot. Normally it's 3 or 4 cents per square foot for encapsulated anchors versus non-encapsulated. So now you're spending $200 plus a nickel, you're still spending the same $150. So here's the real important point, very important point. A building with encapsulation, this is the way the owner would look at it. And I've actually explained it to owners this way and never once had them say no, never once. The owner says, all right, I'll throw an extra nickel into my $350 versus without encapsulation to get the benefit of reduced long-term risk, of the enhanced durability, less likelihood of downstream lawsuits if a condominium homeowners association gets uppity or whatever. There is major risk reduction and quality improvement by using encapsulated systems, and it adds literally a nickel to a $350 job. So, what's the summary of all of this? Designing for efficiency and cost control is very important. That's number one. And with a cast-in-place concrete building, the most important thing to do there is follow 3 rules. When you're laying out a building, when you're doing the early layout, when the building is still on tracing paper, you think formwork, formwork, and formwork. Because if you think in terms of the forming system and laying out a structure that allows the use of high production formwork, right away you've attacked the single biggest cost item in the building. Because the single biggest cost item in a cast-in-place concrete building is the formwork. If you lay out a building that does not allow the use of high production formwork, you're going to add $2, $3, $4, $5 per square foot real fast. If you lay out a structure conversely that does allow the use of high production formwork, you can save $2 or $3 or $4 or $5 per square foot very quickly. So that's number one. Cost control clearly is very important, but once you've done a good, clean, efficient, buildable layout for the building, then you can afford to throw a little more money into the first cost if the ROI is there. And for some of the debates that we get into, like encapsulation, the ROI is there. In my opinion, the debate over the use of modest amounts of bottom rebar in a 2-way flat plate, the ROI is there. If you throw an extra quarter or 30 cents at the most, 35 cents maybe top end per square foot into a 2-way flat plate, you put in a bottom mat, modest amount of rebar, number 4 is at 36 plus or minus. You do the owner a real service. You enhance the quality of the building, you create better life cycle cost, you reduce long-term risk, the potential for cable breakage 10, 20, 30 years down the road, 50 years down the road, whatever. It pays to do certain things up front, build in a little more first cost, and provide the quality that our industry is endeavoring to provide, as Mark very clearly explained earlier. So the final point, life cycle cost and risk management are more important than first cost. Most owners do understand this, and when the message is conveyed properly, they're more than happy to pay for it. The PT industry is a very mature industry now. PT is here to stay. We don't need to worry about it being supplanted by something else. And I think that looking into the next generation of PT design, the message should be still on cost control. We still need to control cost, but I think we need to broaden our focus to include quality, as Mark articulated clearly earlier. Thank you very much.